Hey everybody, this is an AP Physics C problem actually from 2014, but there's no calculus in this one, so it's pretty useful actually to practice here in class, and it's got a good review of a lot of different topics in here. So it says that we got this large circular disk of mass m and radius r is initially stationary on a horizontal icy surface. A person of mass m over 2, so the person's got half the mass of the disk, stands on the edge of the disk. Without slipping on the disk, the person throws a large stone of mass m over 20 horizontally with speed v0 from a height of h above the ice in the radial direction there, meaning just straight out from the center. Shown in the figure is above. The coefficient of friction between the disk and the ice is mu. All velocities are measured relative to the ground. So the time it takes to throw the stone is negligible. You basically push it off right away. Express all answers in terms of m, r, v0, h, m, and fundamental constants as appropriate. This problem that I have set up here, I took off part of it that I'm going to solve here, so the r is not really going to matter. This is also a rotational problem, but we're going to ignore that part for now, so r won't make a difference. All right, so anyway, derive an expression for the length of time it will take for the stone to strike the ice. That is simply a horizontal projectile question. So remember, the useful equation is number 3 there. The vertical displacement is the initial vertical velocity times time plus 1/2 times the vertical acceleration, which is g times time squared. There is no initial vertical velocity for a horizontal projectile, so that drops out, and that gives us that the time to fall is the square root of 2. Our vertical distance, they're just calling h over g. So just a good reminder, and by the way, that square root comes all the way down past the g. A good reminder of the time it takes for something thrown horizontally or dropped from rest to strike the ground there. Okay, so next question. Here's where we get into some momentum stuff. It says, assuming that the disk is free to slide on the ice, derive an expression for the speed of the disk and the person immediately after the stone is thrown here. All right, so this is conservation of momentum. We essentially have an explosion here. So the initial momentum of the system is equal to the final momentum of the system. Well, the initial momentum of the system is 0. So that means our final momentum has to be 0. And what's in our final momentum? Well, we've got the momentum of the disk and person, I'll call it, going back one way, and that is added to the momentum of the stone going the other way. So if those two added up equals 0, then they must be equal to each other. So let's set that up then. So the momentum of the stone is equal to the momentum of the disk person object there. And so now we can plug in for each of these. The momentum of the stone is the mass of the stone, which I'll plug in for later, times the velocity of the stone, which they call v0. And then for the disk person, it is the mass of the disk plus the mass of the person times their velocity, which is what we are trying to solve for there. Okay, now let's plug in a bit more of the details, because they told us that the mass of the stone is just simply m over 20. So m over 20 times v0. And then over here on the right-hand side, the mass of the disk is m, and the mass of the person is m over 2. And so now we're getting closer to solving for what we want here. Let's now add these two together. 1 plus a half is 1.5. So now we have m over 20 times v0 is equal to, let's just write it as 3 over 2m times this unknown velocity. We can see here that our masses will cancel out. So it's the ratios that matter, not the actual number there in terms of determining the final velocity. So now let's get this v by itself by multiplying each side by 2/3. So our final velocity of the disk person will be 2/3 times 1/20th left over from here times v0. So this 2 will simplify this 20 down to a 10, and then the 10 times the 3 will give us 1/30th of the initial velocity of the stone there. Okay, so last one here, it says derive an expression for the time it will take the disk to stop sliding here. So this is now a work energy theorem problem. So now let's write this down here. So, sorry, not a work energy theorem problem. That would be if it was the distance. It is the time to stop. So it is an impulse momentum theorem question. So we are going to change the momentum of the disk in person. So that means we are going to deliver an impulse to them, and that means we're going to exert a force over a time. Now, I'm going to write the mass generically until the end and then plug it in to keep things simple. So the change in momentum of the system will be mass times the change in velocity. And this force right here, it's the force of friction. So that means it's going to be mu times the normal force. Well, on a flat surface, the normal force will be equal to mg times t. So we can see here now that this mass here cancels out with this mass right here, and we are close to plugging in here. So let's rearrange this. So the time to stop sliding then will be equal to the change in velocity over mu times g. So here we have to bring our change in velocity back in here. So we have our velocity that we solve for, right, that the disk started going backwards at. By the way, they do say find the speed of the disk. So when you're solving for this, you might say, well, that's negative because it's going backwards, and you're right. But because they say find the speed, you don't need to worry about that negative. But anyway, this is the speed that it started going backwards with. So that is what we started at, and then it's going to slide to a stop. So this is also equal to the change of the velocity. Starts at this, ends at 0. So coming back to here then, our change is going to be 1 over 30 v0. That is our change, all over mu g. So if we just make that look a little bit prettier, then we'll get v0 over 30 mu g is the time to stop sliding there.